This dam is so large that, in a theoretical NASA calculation, filling its reservoir would make every day on Earth slightly longer. Not by a second, not even by a millisecond, by roughly 0.06 microseconds. That number is microscopic, but the fact that a human structure can appear in a calculation of planetary more than 2.3 kilometers across the Yangtze River and rises 185 meters. Behind it sits a reservoir extending hundreds of kilometers upstream. The power station has 34 generating units with a combined capacity of 22.5 gigawatts. But electricity is only one part of the story. This structure was designed to control floods, transform shipping, and reshape an entire river valley. To understand the rotation claim, imagine a figure skater. When the skater pulls their arms inward, they spin faster. When they extend their arms, they slow down. Earth follows the same basic rule. Moving mass farther from the rotation axis increases the planet's moment of inertia. The Three Gorges Reservoir can hold roughly 40 cubic kilometers of water. Moving that much mass to a higher elevation changes its distribution by a tiny amount. NASA scientist Benjamin Fong Chao used the reservoir as an example after the 2004 Indian Ocean earthquake. His estimate was not a stopwatch measurement proving the dam changed time. It was a physics calculation. If the reservoir were completely filled, the redistribution of water could lengthen a day by about 0.06 microseconds and shift the rotational pole by roughly 2 centimeters. Viral posts often turn that into, "the dam changed Earth's axis." The accurate version is smaller, stranger, and more interesting. The predicted effect is real in principle, but far below anything a person could feel. The dam's visible scale is easier to understand. Its concrete wall is longer than 20 Eiffel Towers laid end to end. Water passing through its turbines can generate more power than many national grids. In the first quarter of 2025 alone, the plant produced about 14.8 billion kilowatt-hours. Hydropower can replace some fossil fuel generation, but a reservoir this large also creates environmental costs that cannot be hidden behind a clean energy label. Inside the powerhouse, the numbers become mechanical. Water enters through giant intake channels and falls through turbines, converting gravitational potential energy into rotation. Generators then convert that motion into electricity. Because river flow changes by season, output is never simply the nameplate capacity multiplied by every hour of the year. Operators must balance power demand with flood control space, navigation requirements, downstream water supply, and the limits of the reservoir itself. The dam is not a switch. It is a constantly adjusted system. Construction demanded a system of its own. Engineers diverted the Yangtze, excavated foundations, poured tens of millions of cubic meters of concrete, installed turbines larger than houses, and built transmission lines to move electricity toward distant cities. Each stage depended on the previous one working before the river could be closed. A skyscraper can rise floor by floor while the street beside it remains. A dam must eventually confront the full force of the river it is replacing. The Yangtze has always been both an economic artery and a flood threat. NASA's Earth Observatory notes that 20th-century floods along the river killed an estimated 300,000 people. The dam can hold back enormous volumes during dangerous peaks and release water later. During major floods in July 2024, the reservoir intercepted more than 12 billion cubic meters of floodwater. That protection is one of the project's strongest arguments. But stopping a river creates a new problem. Ships still need to cross the wall. The solution looks like infrastructure from a science fiction film. Large cargo vessels use 2 parallel, 5-stage lock systems. A ship enters one chamber, the gates close, and the water level changes. It then moves into the next chamber and repeats the process until it has climbed the height difference. Smaller vessels can take an even more dramatic route. The world's largest ship lift. A ship sails into a water-filled steel chamber. The entire chamber, water and ship together, is raised vertically by 113 meters. It uses 256 steel cables and a rack and pinion system. The lift can carry vessels up to 3,000 tons and complete the passage in around 40 minutes, far faster than the multi-stage locks. The chamber must remain level while thousands of tons of water shift inside it. Counterweights carry most of the load, while gears keep both sides synchronized. According to the operator, height deviation is controlled to within about 2 centimeters. If one side climbed faster than the other, the water surface would tilt and the forces would multiply. The precision is what makes the spectacle possible. The largest moving object is not the ship, but the artificial piece of river being carried with it. The navigation system changed the economics of inland China. In the first half of 2025, more than 81 million tons of cargo passed through the locks, and the total throughput of the project exceeded 83 million tons. Demand became so high that China launched another multi-billion-dollar expansion in 2026, adding new locks to relieve the bottleneck. The dam did not merely interrupt the river. It turned the river into a controlled vertical highway. That control came with a human price. The rising reservoir submerged towns, farmland, archaeological sites, and entire landscapes. More than 1 million people were relocated. For some residents, new housing and infrastructure created opportunities. For others, relocation meant losing land, community networks, and a physical connection to family history. No power figure can fully represent that cost. The reservoir also slowed the river and changed how sediment moves. A free-flowing river carries sand and nutrients downstream. A dam traps part of that material, which can reduce reservoir capacity and alter habitats far beyond the wall. Pollution entering tributaries can also accumulate in slower water. Operators now conduct sediment flushing and ecological regulation releases, but those measures manage the consequences. They do not restore the original river. Then there is geology. Large reservoirs add weight to the surface, and water can enter cracks in rock, changing pressure along existing faults. Scientists call the broader phenomenon reservoir-induced seismicity. It does not mean a dam simply creates a giant earthquake from nothing, and evidence at any specific site must be assessed carefully. But it is one reason enormous reservoirs require continuous monitoring of slopes, faults, water levels, and landslides. So how should we judge Three Gorges? By electricity generated, flood damage avoided, cargo moved, people displaced, ecosystems changed? The honest answer is that all of those measurements belong in the same equation. The dam is simultaneously a power station, a flood barrier, a shipping machine, a landscape transformation, and a political statement about what centralized engineering can attempt. And that brings us back to the length of a day. 0.06 microseconds is not a practical consequence. It will not affect clocks, satellites, or your sleep. It is a scale indicator, a way of saying that the water stored behind one wall is large enough to appear in the same physics used to describe earthquakes and planetary motion. The Three Gorges Dam did not stop Earth. It did something more revealing. It showed that when humans move enough mass, even the planet's rotation enters the engineering conversation. The real question is not whether we can build at that scale. We already did. The question is whether we can measure every consequence with the same precision.